okay, did the first part correctly. So obviously that was already done in class, so you've done it correctly, and I appreciate that. And you got full marks for that. So that question had 3 marks for the first part of the question and 2 marks for the case when it was massless. So in the massless case, our action, which is a functional of the coordinate x bar, the momentum p, considered independent of the coordinate, and this auxiliary field E, okay, they're all functions of tau, and our action in the massless case, so this is m equal to 0. So first of all, many of you did the first part correctly, and then you said, oh, if you put m equal to 0, the action vanishes, and so that's where the buck stops. Now we had mentioned in class that would be stupid, right? Then I wouldn't deal with this first order problem. So obviously, those who did that did not attend my class or would have forgotten what we did in class. The idea was that if you go back to this, minus half E p squared, and then there was this minus m squared c squared in the massive case, right? And then, of course, you were supposed to first do a variation with respect to p, get the equation from the equation of motion for p, eliminate p, plug it back into the equation, then solve for E, and then plug it back. And then you found that you had 2 solutions, and one of them only had the correct non-relativistic limit. So that was the answer. That everybody has done correctly. On the other hand, the question was, what if this is 0? Which step would you stop at? Well, let us see that. So when you first do the variation with respect to p, so you follow the steps. And some of you did that. And of course, they got full marks. This is delta p dot u, right? Minus the half cancels because there's a p squared, and it's p dot delta p. So this implies that p u by e. Straightforward, right? Just from this equation. This is equal to 0, and therefore p is u by e. Okay, so I plug that back in here and also here, and I get my so from here I get my action S1, let us say, which is now a functional of only x and e, x bar and e. Okay, so this becomes just half integral d tau e inverse u squared. So far, so good. But then you realize that because there is no other term involving E, if you take the variation with respect to E, you get U squared equal to 0, which is something you know already, right? That's not the end. So you can't actually solve for E from here. So that was the difficulty that I wanted you to identify, that you cannot solve. So the difficulty here and this would have fetched you 2 marks. Delta E s equal to 0 does not imply closed form solution for E. That is what I was looking for. Some of you did that and then you got full marks. Some of you didn't and you got 2 marks less for E. So I'm going to now discuss what you do in this stage, okay? That's the point of this part of today's discussion. Now look at this equation. So we look at S1, okay, half so everything is a function. E is a function of tau, U is a function of tau, right? And what I'm going to do is to show you that this action, has an invariance. So if I change tau to some tau prime, which is equal to any arbitrary function of tau, of course, smooth function of tau. Suppose I do that, right? Then, of course, d tau becomes d tau prime. And if tau prime is a function of tau, then this is obviously f dot of tau d tau, right? Obviously, right? And also u. So let us look at u. U is nothing but dx bar d tau, right? And x, of course, is a coordinate in space-time, so it's a function of tau, but it's a scalar function of tau, if you wish. It does not change anyway. So we can write this as dx bar d tau prime f of tau, right? But this is f dot, sorry. dt prime by d tau is f dot. Okay? Now this quantity here, okay, that has a certain feature. So there is a way that this transforms in such a way that this is equal to half d tau prime E inverse of tau prime u squared of, so this is tau here, and this becomes same. In other words, when I change the parameterization, the action stays invariant. So this is like some sort of a gauge transformation, if you wish, that changing tau to any arbitrary function of tau does not change the action. But this will be true provided. So let's begin with this one. Let's begin with the tau prime and see that it gets back to here. So this will get back to here provided. So this is, so d tau prime, now we just write down these formulas, right? So d tau, then there's one f dot coming from here, but there's another f dot coming from here, so there's f dot squared of tau, E inverse of tau prime. Now E, okay, E is a field which does not live in space-time. It's a field which lives on the curve. So I have to change this and tell you how E should transform in such a way. Oh, sorry, I've forgotten the U squared. Okay. So what happened? Sorry. Yeah. So U squared. So how will this transform? This will transform. Sorry, there's a mistake I made somewhere. Hang on. So yeah. So in fact, so from here we can write. I'm not completed this one yet. So U of tau prime f dot of tau. Okay, so yes, this is the point. So U of tau prime is equal to U of tau Oh, what's happening to this? U of tau divided by F dot. So there's a dot here. F dot of tau, which implies that U squared of tau prime is equal to U squared of tau divided by F dot squared of tau. Okay. So now the question remains how this should transform, and we can figure that out, how this should transform in such that. And I wish I could tell you a little more about this, but that will have to wait till you understand a little bit of gravity. So let's see, what did I do wrong here? Hang on. Yeah. So here, here I have, let me rewrite this. This was a mistake. So I get 1 f of tau from d tau prime. So we begin with this expression and write it in terms of tau. And if we get the same expression back, then we are okay, correct? Right. Okay, so here, what we have is d tau. From here we get f dot. I'm not writing tau because f is always a function of tau. From u squared, we know we get a u squared by f dot squared. And now this is a function of tau, right, from here. Because, yeah, so u squared of tau prime is u squared of tau divided by f dot squared. So there's a dot here. So 1 f dot cancels with this here. And then we have E inverse of tau prime. Okay? So this is an invariant only if E inverse of tau prime is equal to E inverse of tau times f dot of tau. So if we take this to be our transmission property for E, in particular E inverse, which is the same thing as saying that E, which is a reciprocal, E of tau prime is basically E of tau divided by f dot of tau. Okay, so if this is the transmission property, then this action is invariant. It's the same as the one I wrote on top. Okay, so that's the action. Now, with this kind of a transmission law, so that then we can see immediately that our action is invariant when I change the affine parameter, which describes motion, which describes a point on the curve followed by this particle, followed by the charge. If I change to any function of the parameter, it's a general coordinate transmission if you wish, then this way, this kind of a transmission will lead us to a reparametrization invariant action. So this is what is called reparametrization invariant. It's a long word.
Sir,
Yeah.
so in the question paper, the question was little different. It was asked that it was a derive the standard form of the action STD means square bracket x that we have derived, and if we set m is equal to 0 at the onset, what problem does one face to derive the action is a standard. It was not
That's right.
it was a standard. So
That's right. So the problem was no. I think there was a misunderstanding. So the idea was that if at the outset you set n to 0, can you get an action like a standard?
but that was not written. Means it if
That
it
was
was
the
written,
question. That was the question. Otherwise, what is
oh,
there in the question? Should I ask you what happens when you put m equal to 0 in the standard form? That would be an idiotic question to ask, don't you think?
but okay, but it was written now. Means what problem does one face to
Yes, yes. What problem?
derive an
And this
action?
is the problem. You can't get a closed
Acha,
form
acha,
solution for E. That's the answer, right?
acha, acha.
Okay.
Hmm.
So the idea was that I know one way of getting the standard action from here when there's a mass. But when there is no mass, what do I do? And that is the question. So the difficulty is you can't form a solution for E, and because you can't form a solution for E, you can't get a standard form of the action, which only involves the coordinate. What do you mean by a standard form of the action? A standard form of the action is one when there are no extra fields anymore. You have eliminated the extra fields by solving their equations of motion, right? But you can't do that here because of this. But now I'm going to show you that because of this reparameterization invariance, you can actually do that here. You see, E is an auxiliary field. It's a Lagrange multiplier. All of you will agree with that. And all of you will agree that Lagrange multipliers I mean, this is from classical mechanics. Lagrange multipliers have no physics. In other words, they do not describe, by this I mean, they do not describe propagating degrees of freedom. Is this known to you or not? My statement is that Lagrange multipliers do not correspond to propagating degrees of freedom. Is that known or not? Is there anyone who does not know this for a fact? I mean, you have done the theory of constraints in classical mechanics, and in that you've seen that you need these Lagrange multipliers in order to write down an action or Hamiltonian. But otherwise, the Lagrange multipliers, yeah, so you want to write down a Hamiltonian with constraints, you need Lagrange multipliers. But intrinsically, Lagrange multipliers have no physics. Is that correct or not? Hello? So I assume that this is known to all of you. Can you hear me? Hello?
Yes, sir.
Hello?
Yes, sir.
Yeah? Shafaq, can you hear me? Raj?
Yes, sir.
Yes, sir.
So is this known to you, right? This is Rupsha,
Yes,
Lavani,
sir.
Shohini, all of you will know this, right? Which means that there are no propagating degrees of freedom. Now, what we notice here is this. Okay, so we have a choice because we can choose this function.
Sir, I have one thing to say. I mean, I don't know if I remember it correctly, but somewhere I learned that these Lagrange multipliers give the constraint force or something. I don't really remember, but is that what you mean?
Yeah, I mean, see, it all depends on how much you have worked with Lagrange multipliers. Here, for instance, if we look at this equation, or even the massless equation, this one, sorry, yeah, when mass is 0. So if you look at this action, the first action, and make a variation with respect to E, you get the constraint p squared equal to 0, which we know is the right constraint for the massless particle, right?
Yeah.
Okay. However, does E have any propagating degrees of freedom? The answer is no. Okay. And that's what I'm trying to show you now is that actually
What
using
is
this.
propagating degree of freedom? What's that?
Oh, a propagating degree of freedom is a degree of freedom which has a tau dependent equation of motion
Like
with
E of tau
derivatives.
here.
Yeah. Is there an equation with derivatives of E? See, a propagating equation of motion, for instance, would be an equation for the acceleration of a particle.
Okay, I see.
Okay. Which involves the derivative of U. But there is no such equation. Right? So what I'm going to argue here is that every Lagrange multiplier, okay, is like, in gauge theory, it's called a pure gauge. I can make a choice. So F was a reparametrization. Okay. So now you can see that you can write this equation in the opposite way. You can write E of tau as F dot of tau tau prime, let us say, just inverse transform times E of tau prime. So if you make an inverse transform, E of tau is that, and then you see, once we have this, you can see that I can choose F dot of tau prime to be equal to E inverse tau prime. I can make a choice. So that's like a gauge choice. It's a choice of a parametrization choice. Because I never said what f is. F is an arbitrary function. So suppose I choose an f whose derivative with respect to tau prime is just E inverse of tau prime, then E of tau becomes 1. So this choice, what it does for me is to reduce E of tau is equal to 1. Now, this is the point. You can always make a choice of a Lagrange multiplier depending on its transformation law. So, given the fact that the action is invariant, the action couldn't give a damn about what function f of tau I chose. So, I choose an f of tau, which is the inverse of tau prime. You can turn it the other way around, it doesn't matter. You can always go from the last step to the first step, okay, and choose the function f in such a way that the new e becomes equal to 1. So with this choice, you see what happens is S1, well, now we get an S2, or I can still call it S1 bar, which is only a function of x bar. And what is that? That is nothing but g tau u squared of tau with a half. So now we have indeed with this choice, see, that is why I decided to work this out for you because it's not done anywhere. But we found that there is a kind of transmission law which allows me, okay, to choose this quantity E because the E is a Lagrange multiplier. See, I can't do it with U. I can't do it with anything else. Well, I have only two things, U and E. U is dx d tau, dx bar d tau. And I can't choose that because X is, of course, the dominant degree of freedom. But E has no physics, Lagrange being a Lagrange multiplier, and therefore I have the liberty to choose it. And I choose, because of this, I can choose a parametrization in such a way that U of tau is 1. Of course, this is a parameterization. Now my parameterization is fixed. My tau is fixed. So if I choose f prime of tau, f dot of tau to be E inverse of tau, my parameterization is fixed. Okay? But that also fixes my Lagrange multiplier to be something which is very simple, giving me this as the action. Okay? So you see, this is not the same action as in the massive case. There is no square root. There is no square root in this action. Okay. However, I can now solve for delta x bar. I can make the variation s bar 1 equal to 0, and this implies expected result A equal to 0. So there is one mistake that I have made here. Well, it's not really a mistake. It's what tau is. You see, in the massless case, tau is not the proper time anymore. Why is that not? See, in the massless case, tau not the proper time. The answer is very simple. Tau is still a parameter which is arbitrarily chosen. It does not depend on any coordinate, but it does not have the interpretation of proper time. Why? Because just carry on, just remember what tau was in the massive case. In the massive case, when m not equal to 0, tau corresponds to time measured in the rest frame, right? But as you all know, when the mass vanishes, the particle does not have any rest frame. So what do we mean by time measured in rest frame if there is no rest frame? So that is why, although I keep writing it tau, some books say that you should not write tau because some people might be confused that tau is the proper time when there is no proper time in the massless case. In massless case, when m equal to 0, right? Tau not proper time. What is it? It is any parameter. But I cannot talk about time in the massless case. This is something we had discussed in class. You see, time makes sense only when you have mass, right? So that's the thing about our time, about our light frame. So we can talk about, so you see here, when we write down time, you can talk about a particle going like this or so on, and you can talk about time, right? Various times. But when you talk about light, you see, there is no such thing as time. I mentioned this earlier that it's as if the entire light ray is accessible to you at the same time. There is no such concept of time because to get a concept of time, we need a rest frame. And the rest frame simply does not exist for a massless particle because it is always moving with the velocity of light. So I hope this argument is clear. Of course, you will ask questions if it is not clear. So that is why I use the same parameter tau as a symbol, but I've clearly mentioned, and this is something that you should remember, that in the massless case, tau is not the proper time. I should put inverted comma because there is no proper time. Okay? There is no proper time. Proper time is only meaningful as a physical interpretation in the situation when there is a mass. However, I will, every curve, you see, every trajectory of a particle, massive or massless, will have a continuous parameter which keeps changing along the curve. Tau is that parameter. And we have seen that in the massless case, we have this reparameterization invariance, which allows us to choose E to be equal to 1. And of course, once we choose E to be equal to 1, then we have this property which is, of course, known. Okay, this is completely known that A, the acceleration of any massless particle must always be zero. Okay? So that's really the point that I wanted to make as far as this is concerned. So any questions on this, please? Before I go on to our original topic, is there a question? All right. So I hope now I have convinced you that in the massless case also there is a proper action. There was already a proper action, but that involved this auxiliary Lagrange multiplier. And now we have shown, because of reparameterization invariance, how you can choose the Lagrange multiplier, and therefore you can actually derive the equation of motion for a massless particle. But the equation of motion is nothing unexpected. It simply says that a massless particle can never accelerate. Okay? And this is one of the reasons why I told you that everything which carries charge must have a mass. Because if it did not have a mass, then I could make the particle accelerate by applying an electromagnetic field. But the acceleration of a massless particle is always zero in special relativistic spacetime, in Minkowski spacetime. The acceleration is always zero. On the other hand, we know that if the particle has mass, then the acceleration need not be zero. In fact, that is what we're going to do now. Okay? So I hope there is no confusion on this anymore, exactly what was asked in the physics in the question and what people did. But I want to make one comment before I go on to our topic of discussion today, and that is the following. I found that there are some questions on which people seem to have done some kind of a collaboration. In other words, people, were writing the same sort of words for answers to some of the questions. Okay? And even when they're space-like separated, I could not understand this coincidence. Now, maybe those who have come to class today do not fall into that group. Maybe there are others who fall into that group. And I must say that in many cases I've given the benefit of doubt. I've not deducted marks. But on the other hand, in some cases, even the mistakes are common. So I would like to remind you that an exam is not a collaborative effort. So those of you who decided to collaborate during exams should be warned, because I have in my mind the names of those persons who actually did this. And next time I shall be very careful and I shall penalize those who did this. And I shall also bring their names to the attention of the authorities, which means that their careers may be in trouble. Because this is deemed to be a very culpable offense. So most of you actually did not do this, but those of you who did, I don't want to give out my suspicions about who did this, but some of you did do it, I know for sure. I'm simply issuing a warning that please don't do it next time. Okay? If you want to talk about it, if you say that, oh sir, I can't help myself, I have to do this, otherwise I'll have a nervous breakdown and so on and so forth, I am willing to do some counseling for you, to sit with you over a Google Meet just with you and have a discussion. So if you feel that you need to do this, I shall try to sit with you and persuade you that you do not. Because I think most of you have been, well, I shouldn't say most, but many of you, well, the majority of you probably, yeah, certainly a large majority of you have been attending my classes, asking questions, doing the assignments, and doing things in the regular way, so you'll have no difficulty. But those of you who decided See, the way I would know this is because if you are consulting each other, or indeed, what is a very common practice in some places abroad is that you think there is some expert. I mean, this is the way I figured it out. You have answered a question where, well, some of you, one question was not answered by most of you, and that is the question on field theory. But some of you did try to attempt that question, and among them, some were using a notation which we did not use in class. And I've noticed it right away, right? Because I know my notation, and you also know your notation. So you were copying from probably somewhere on the internet. Now, those of
Sir,
you who
I
did it,
sir,
yeah,
this is
yeah,
Ritesh. I use the variational notation in field theory because I knew it. I studied it.
who are you?
Ritesh.
Ritesh. No, no, Ritesh, you don't have a problem. I'm not talking about you. Uh, yeah, so I'm not talking about Ritesh. Ritesh did very well on the exam. So one of the high, I think he was one of the highest. So obviously there's no problem with that. But on the other hand, I'm talking about some other people. I think they know who they are. I don't want them to come up. I don't need to talk to them right now. But you see, when I follow some notation, and if you do not have any objections, I assume that you are following the notation. You have no difficulty. But on the exam, you're using somebody else's notation. Now, this parallel teaching, I have a problem with. Okay, because you are answering part of the exam paper in my notation and some other part in somebody else's notation. That is unacceptable. If you have a uniform notation, it need not be my notation, but it should be a uniform notation. On the other hand, if you do have some questions answered in my notation, in that case, I expect that you would answer the other questions also in my notation. Now, if you consulted only your notes, which is the only thing I would allow you to consult, even though even that is forbidden by the authorities. But if you did consult your notes when you were doing the exam, I have no issues with that. On the other hand, if you are consulting other students or some third party like the internet or some other person whom you consider as the world expert on field theory or something, in that case, I would take strong exception and ask you to join that person for this course rather than my course. I think you will admit that this is a fair statement. Okay? I think, see, Ritesh, you actually followed my notation. I'm perfectly all right with your work. I have nothing to say. Because you,
Sir, but you didn't introduce the variational approach too. Means, I mean, if we are given field to field,
that's
then
fine, that's fine. The variational approach is what I always follow. I always,
yeah, but
your audio
you
is very
didn't.
bad. Can you turn it off? Hello, Ritesh, turn off your audio. It is very noisy. Yeah. Ritesh, your audio is extremely noisy. There's some background noise. I don't know why that is coming. But anyway, there is the variational approach is exactly what I followed and what you followed, and some others who got full marks on the thing also followed. So you don't have a problem. I don't have a problem with that. But there are some people who actually wrote something wrong. And there are some people who wrote the same wrong things. When people commit the same mistakes with the same notation, then I smell a rat. So let's stop this. I don't want to carry on and on with this issue. But I'm just saying that please don't do it in future. Because you see, one thing you must realize, whatever you do on your own is what you've learned. And whatever you copy is something you will forget and you have not learned it. You can't say that, oh, I'll pick it up later on, because you will not. If you have not learned something, but you're trying to copy it for getting a better mark on the exam, that itself is a sign of failure. It is better not to answer a question than to copy from someone just to get good marks. It is better because it is more honest. And honesty lies at the heart of science. If you are dishonest, I would suggest you give up science immediately. You have no right to be in science. Okay? Right. So, with that, let's go on to the next topic of discussion. So, what we were doing is, we did derive this formula, right? And I told you that this is not there in textbooks. And I can't remember the formula. It was q squared divided by some c to the fourth, I think, a squared ua d tau. Is this correct? Is this correct? This
Yes,
is the
sir.
forward momentum of an accelerated particle, right? So this immediately leads us to, so this is the radiant part, right? Rad. So this leads us to d E rad, the radiant energy, which is the zeroth component, and that is equal to minus 2 by 3 q squared by c to the, it should be c cubed, right? Q squared by c cubed, right? A squared. And if you put a equal to 0, this index a equal to 0, which is what gives you this, then that gives you gamma c. So that takes care of one of the factors of c, and the gamma d tau simply gives you dt, the coordinate time. Okay, so that's what, so from here we know that, so that also leads us to the, I mean, it's a total intensity, which is I rad is dE rad dt, which is equal to, oops, sorry, I can't rush with this board. Minus 2 by 3 q squared by c cubed 4 acceleration squared. So that is the formula for the total intensity of radiation after you've integrated over angles. So the integration over angles is what we did in the relativistic case in the last lecture. Okay? Is there any question about that derivation, or have you not had time to go over that derivation? Yeah? Anyone? Let's say Ruksha. Did you go over that derivation, ma'am?
No, sir. Not didn't get the time to do that, but we'll do it soon.
Okay, but I would suggest to all of you that you should derive that expression, this expression here, of dPA d tau. Okay? If you can derive it without looking at the notes, only then you can claim you've understood it. So that's an exercise. Should I put it as an assignment, you think? But I did the whole thing in class, so what's the point of putting it as an assignment? Okay, but you see, I think you should have a discussion on that with Horitro in case you wish to have some difficulty. You have some difficulty. So I would expect you to at least go to the derivation before this Friday. But I will give you an assignment soon. I'll give you an assignment which you can submit after Friday. Okay, so that's it. Now, what we want to look at is the following situation. We want to look at a situation where the charge Q is accelerated by an external F bar AB. So I'm calling it F bar AB to distinguish it. So I'm putting a bar here to suggest that it's an external force. Now, there was a question which Raj raised about an action. See, Raj, there is absolutely no problem. I mean, I already gave you the answer, so all of you may have seen the answer, that this is a typical situation in an accelerator laboratory. In an accelerator laboratory, you have charged particles like protons at the LHC, at the Large Hadron Collider. You have protons which you want to accelerate. And for accelerating charged particles, you need external electromagnetic fields. But once these charges accelerate, they produce fields of their own which are much, much larger. And these fields, okay, is what is described in this radiation formula. And because you're accelerating the particles to very large velocity, and there are zillions of particles there are crores and crores of particles of protons in the LHC tunnel. You see, it's very dangerous when the particles are accelerated and moving in the tunnel. You will not be allowed anywhere near the vicinity of the tunnel because tremendous amount of electromagnetic radiation described by our formulas here is coming out of that tunnel. Okay, so what they have is huge 2 or 3 feet thick concrete blocks set around the tunnel, and all observers are supposed to be on the other side of the concrete blocks. The concrete blocks, the work of the concrete blocks is to absorb the electromagnetic radiation. It's called shielding. So the shielding is not only for the observers, for the human observers, but also for the external electromagnetic field sources. These could be huge magnets or whatever, capacitors, Van de Graaff generators, what have you. These have also been shielded because the external radiation will damage everything. So external radiation in particle accelerator laboratories is a huge problem, and some of you, who have an applied engineering orientation may want to work on that in future. It's a huge business. So everywhere, wherever there are accelerator laboratories, in Kolkata, for instance, we have this variable energy cyclotron center. So if you get a chance, after this lockdown is lifted and so on, if you get a chance, you might go over there and ask for a tour to see what kind of shielding they have. Okay, that's good. So that will give you an idea that what we're talking about is actually very real. Okay. So on the other hand, Raj's question was more theoretical. He wanted to know if I can write down an action. Indeed, I can. Indeed, the action begins by saying I have external electromagnetic fields for which I can write down a Maxwell action, right? And once I write down the action, I know what that leads to. That leads to the particles, the protons, obeying this kind of an equation, which is called the relativistic Lorentz force equation, which is Q by C, F bar AB, UB. Which I can, of course, write as Q by C without any change as F bar A, put the B down and raise the U index up, right? Absolutely no change because it's up down here and I can always write it up down here. Okay, so that's this. And then from here, I can get an expression for the acceleration. And what is that? So this dPA d tau is m times acceleration. M is the invariant mass. And so I get Q by mc F bar A B UB. So now, given that acceleration, what I can do is I can then try to find out the intensity of radiation just here by plugging in A here. Okay? So just by plugging in A here, I can find out the intensity of radiation. And I wanted to do that for you because there are some special cases of interest. So I radiation, which is dE radiation d tau, it's the power radiated. The intensity and this power are the same, is minus 2 by 3, right? So I will need to little, yeah. q squared. So q squared, and then there's a q by c squared coming from the square. Okay, so from here, q by mc squared. So q squared by m squared c squared times this quantity f, right? So let me write that down, 2 by 3. So it's q fourth by c cubed. Well, it's m squared and then c fifth, right? C to the power of 5. Is that correct? See, a squared, if you take the square, this quantity will be q squared by m squared c squared. There's a c cubed, so you get this quantity, q fourth by m squared c fifth, right? Times f bar ab ub, and I shall have another f bar because I'm taking the square of this quantity, ac uc. Okay, so is this absolutely clear? This IRAD formula? Have I made a mistake? Anyone? So no objections are being raised.
Sir,
Yeah.
sir, one doubt about notation. Here, why are we using F bar instead of just F? I mean, is it different?
Oh, because I'm keeping the F for the radiant fields.
Okay, sir.
Okay, so just to distinguish between the fields which are produced by the magnets and the Van de Graaff generated in your laboratory from the fields from which you're trying to shield yourself, radiant fields, I'm using two different notation. Okay, so that's the idea. You could actually do away with that. Some people do away with that. Some people use EXT, external. But I just have to say that yes, they are external fields acting on the particle. Right? All right. So now we have to. What I would like to do is to express this in terms of E bar and V bar, in terms of the electric and magnetic fields. Because in the laboratory, that is what you're going to create. You see, it's all very nice to write down these relativistic formulas, but when you go to the laboratory, you will always use E and B, okay, in the three-dimensional sense. So some people like Jackson do not want to use this F bar too much. And there are great people like Julian Schwinger, the Nobel laureate, who also said that I would like to use notation which you directly use in the laboratory. But my point is, I would like to do the calculations in a relativistic way. And then once I've done everything in the relativistic way, that is a good check that I'm doing things correctly. Once everything is correct, I know that I have the relativistic formula. Going to the non-relativistic formula, I mean not the non-relativistic, I mean three-dimensional vector formula in terms of E and B is not a big problem, right? And that's what I'm going to show you now. It's not a big problem. So the quantity that I want really to consider here is just this, right? So actually we can carry on with this whole business. So this is minus 2 by 3. I'll be a little slow because not because I'm getting slower in my head, but because this board does not allow me to move fast. Okay, so I'm going to break this up into components, right? So let's first break up into this component. So F. So let's take A equal to 0. So there is a summation over A, summation over B, summation over C. So first I shall do the summation over A and choose this to be 0, right? So choose this to be 0. And then of course B will have to be beta, right? And similarly here, F bar, if I choose A to be 0, like here, I have to choose if this is a 0, this is also 0, then this has to be gamma, u gamma. So that's one term. And then I choose A to be alpha. If I choose A to be alpha, then I have AF alpha, but then B can be 0, right? So if you just look at one factor, this factor, then F alpha 0, U 0. So this is 0. I'm writing this to be 0. but that's only one term, because I can also get a term which is F alpha beta, and then I must have U beta. So that's the first factor. And the second factor will be very similar, F alpha 0, U 0, right, plus F, sorry, I've forgotten the bars. After announcing the bars, I've forgotten. Alpha gamma Okay, so you see, it's a peculiar arrangement of terms. Now I'm not going to do the math anymore because you all know everything. You all know how to raise and lower time-like index and space-like index. So I will simply write down the formula. So let me look up the formula from my notes. So this is exercise. So I'll pick up my notes and copy the formula. It's a nice little formula, and it gives us 2 by 3 q to the 4th gamma squared m squared c cubed into e plus beta cross b quantity squared minus e dot beta. Oh, I'm forgetting the bars here. Bar, bar, bar. Okay, so all you have to do is remember in the Gaussian units what the F's are in terms of E and B, and you should be able to derive this. So that's actually a very nice algebraic exercise, and make sure this is the correct formula because this formula is there in Landau-Lifshitz. LL, Classical Theory of Fields. Okay, so this formula is the correct formula, and we have derived it in our own way from our own expression here. We have derived it. This, of course, we know that this formula agrees with Landau-Lifshitz also, so there is no big deal here. We have just gone ahead, used our covariant, Lorentz invariant, Lorentz covariant, Lorentz force equation, Lorentz covariant, Lorentz force equation. That's quite a mouthful, and then we get this formula. Okay. So what I'm going to do now is to discuss a few special cases, and then we shall be done today. We'll carry on the discussion next time. So the first discussion is that we can express this formula for the intensity of radiation, IRAD, express IRAD in terms of it's very simple to do that, EP, the energy of the particle, the energy of the free particle, which is m gamma c squared, of only the particle. Okay, and so that is very easy. All you do from here is write gamma equal to EP by mc squared. So if you plug that in here, IRAD becomes equal to, it's a sort of a trivial statement, but you can do that if you want. It's Q4 EP squared divided by M4 c to the power of 7 times, of course, the same quantity, E bar plus beta cross B bar whole squared minus E bar dot beta. Okay, so the point is that you can directly write the intensity of radiation in the general case in terms of the energy of the particle. Okay. Now I shall consider two special cases. A, when B is equal to 0. This implies, so this term drops out and we have IRAD is equal to 2 by 3. So I'll go back to this formula because I want to show you something now. The same formula really. Okay, and what I have is E squared minus E bar squared, sorry, E bar dot beta squared. So if we have a situation where E bar is parallel to beta, okay, so then this term is simply, so I can take the E squared, capital E squared out, so we get, in this case, this is equal to the rad 2 by 3 q fourth gamma squared divided by m squared c cubed e squared, e bar squared times 1 minus beta squared, right? If they're parallel, only if they're parallel. Okay? So in that case, we see that the gamma squared and 1 minus beta squared, of course, cancel each other out. And we get an expression for the radiated energy intensity, which is independent of the energy of the particle. This E is, of course, the electric field, E bar. So now, if you wish, you can rewrite it, but it doesn't matter. This EP has actually cancelled out because the gamma square is cancelled out. So in this particular case, this is the one case in which if the electric field of a relativistic particle is parallel to the direction of the velocity, then the radiation of the particle, see, the electric field, of course, is causing an acceleration, which we have derived here, the radiated intensity. But then the radiated intensity has nothing to do with the energy of the particle. It's independent of the energy of the particle. So this is independent of particle energy. In the general case, it wasn't because of this, but in this case, it is. Okay, so that's one physical effect which we deduced from this expression. The second physical effect is this. The other one, which is the bar here. Sorry. So E bar is equal to 0. Then, of course, this is no longer true that it is independent of gamma, right? Because you see, well, this formula here. So the IRAD in this case does depend on the energy of the particle. Well, I can write the gamma squared formula without any problem. And this one is simply beta cross B whole squared. Okay? Now this formula, okay, reduces to, so if you have a situation where beta is perpendicular to the direction of the magnetic field. Okay? For instance, if you have a magnetic field, let's say uniform magnetic field, and a particle moving in a circle in a plane perpendicular to the magnetic field, then of course you can write this as 2 by 3 q to the fourth gamma squared divided by m squared c to the fourth, okay, times beta squared times b bar squared. So this kind of a situation, we have calculated the total intensity of a particle moving only under the influence of a magnetic field which is perpendicular to the direction of the velocity. So this kind of a radiation has a name. It's a very important effect. Okay, it's a very important effect, and it has a name. And we shall spend the next class also studying this. It's called synchrotron radiation. Synchrotron radiation is such an important phenomena that it occurs everywhere on Earth, okay? On Earth in various ways. So how? First of all, in laboratories, accelerator laboratories, I've already mentioned that you have a tunnel which is in the form of a loop, of a circle, and there are magnetic fields which are used, okay, to keep it in a circle. So you have a situation where, you know, a large kind of a tunnel like this, and there is a magnetic field. So that's the direction of the velocity. Let's say the xy plane, if you wish, and this is the magnetic field, uniform magnetic field, but very large magnetic field, created by all kinds of magnets, which I can't tell you because I'm not an expert in how to create magnetic fields. But whenever you have a particle moving in a magnetic field and it's moving with relativistic speeds, immediately you will have this phenomenon of synchrotron radiation. Particle is moving in an arbitrary plane, not in plane perpendicular, but then it will have a helical motion, that you know already. So it will have a kind of helical motion. Yeah, please. Oh, you got me. I don't know. I'm not an expert on particle acceleration at all. So I will have to look that up. Okay. So I'm just giving you some basic common sense kind of ideas, which I have heard and I have known, but I don't know what achromatic bend is. But who is it asking the question? To first figure out. Shyam. Okay, Shyam, this is something that you have to do the research on. And I am not even the kind of expert who could suggest to you a good book. So you'll have to do the research on your own. You see, particle accelerators are not a lot in India. There is one in Kolkata, as I said, the Variable Energy Cyclotron Center. So you could certainly talk to people there. I know some people there. I could get you in touch with them after the pandemic is over. And then there are accelerators in Mumbai. Tata Institute of Fundamental Research has an accelerator. These are all nuclear physics accelerators. None of them is actually a high energy particle accelerator. And then there are accelerators in Indore and Delhi. there is no high energy particle accelerator in India. Okay, usually we measure these accelerators by the amount of center of mass energy. Now that's one thing which I have not told you about. So, but I can tell you what the center of mass energy squared is. Okay, this is something which I did not do this time. Last time I had a question on the exam based on this. So let's not get into that right now. But the point is that the center of mass energy squared, you see, if it is less than 1 giga electron volt, then it's not a high energy particle accelerator. It will work for for accelerating nuclei, okay, for low energy experiments. The kind of accelerator we have, the best, like LHC, has a center of mass energy squared of 14 tera electron volts. A tera electron volt is 1,000 times giga electron volt. So you can see it's 14,000 giga electron. It's a huge kind of energy. And we don't have any of that in India. And it's not possible to have an accelerator of that capacity in any country as a kind of thing within that country. It has to be an international consortium. But I would like to say, Shyam, that my other interest in synchrotron. So one interest comes directly that you always have synchrotron radiation in a particle accelerator. In a particle accelerator where you have tunnels, you have circular tunnels. But you also have synchrotron radiation ubiquitously in the sky. So I would say that this is astrophysically very important. Synchrotron radiation is astrophysically very important. Because a lot of stars, especially compact stars like neutron stars, which are rotating, white dwarfs, which are rotating, all these have magnetic fields. And therefore, particles in that magnetic field will undergo synchrotron radiation. So a lot of the radiation that we observe from stars is actually synchrotron radiation. Okay? So it is that was only about stars, but then you go to galaxies, there are galactic magnetic fields, there are intergalactic magnetic fields, there are cluster magnetic fields all over the place. And by the way, the mechanism for these magnetic fields is only partly understood. So one of the open problems, you see, is to take this kind of electromagnetic theory that we have been discussing in this course and to see how such large magnetic fields, which are millions of times of the magnetic field of the Earth, how such magnetic fields are actually generated. What is the mechanism? There are some theories known as dynamo theories, which people mention. Okay? And I've heard a little bit about them, but I'm not into astrophysics of magnetic fields. But that's a very open and very tempting subject because there's a lot of data and very little theory. So one could actually do a lot of work in deriving astrophysics of magnetic fields. But once you have magnetic fields, you see, you will have synchrotron radiation. And therefore, today, the rest of today, I shall begin to discuss relativistic particle motion in a magnetic field. Now that is actually, it's already there if you wish, because we know what the acceleration is, right? And from the acceleration, we can write down an equation in this situation. So we have this kind of a situation where beta dot B is 0, okay? And we can do many things with it. So we shall now spend our time, this class, and probably the whole of the next class on Thursday to discuss synchrotron radiation. Okay? So I've mentioned two areas, but there are also other areas in which synchrotron radiation is important. But there are medical applications and so on and so forth. And in fact, there are medical applications for cancer treatment where synchrotron radiation is actually used for cancer. So when you hear about radiation therapy, the kind of radiation they are using is basically synchrotron radiation in most cases. There's also linear accelerators, small linear accelerators. That's a different mechanism. That's not synchrotron radiation. Synchrotron radiation has to do with circular motion or helical motion in a uniform magnetic field of large magnitude. Okay, so as I said, so one thing we have not discussed in this course is what is the trajectory, or let me just say that what is the trajectory I said it's a circular motion, but I would like to do the following. I'd like to describe for you the derivation. I would like to derive for you of a charge in a uniform B bar. So B bar is a uniform field, like I have written here. So I'd like to describe for you the trajectory. So this is a relativistic charge. I trust that all of you are familiar with the non-relativistic problem. So I'm just going to describe for you the relativistic equation, which you know already, right? And this equation, of course, derives from the Lorentz force equation. So I'm writing the Lorentz force equation. This is still relativistic. Remember, we proved that the Lorentz force equation is actually relativistic, even if you use T here. We have actually proved that, right? Excuse me. I need a little water. Right. Usually I don't talk as much as I talk in a lecture. So this quantity is nothing but Q beta cross B. Now the momentum P, of course, is m gamma V. You all know these formulas, but I can write this in terms of the energy, right? And this is, so energy P V by C squared. Or you can write this as EP by C times beta. So that's the momentum, right? And the energy, of course, is unaffected because the only thing that changes in this motion is the directionality, right? So I can plug this in here and I'll get an equation. So EP by C beta dot is Q beta cross B. Okay, or beta dot, this is an equation for beta dot, QC by EP, the energy of the particle, times beta cross B. And now I can write my components. So if we imagine B, oh, I've forgotten bar. So all these are bars. So if B bar is equal to, right, let's say some B bar magnitude times EZ. So so the Z direction is in the upward direction in the picture, right? Then we can get from here beta dot x, for instance. What is that equal to? QC B bar by EP. What do you get here? So it's YZ, so beta Y, right? And beta X dot, beta Y dot. What is beta Y dot? So it's again QC B bar right? Minus beta X, correct? Is that correct or not? Okay. If there's no objection, I must assume that it is correct. And beta Z dot, what is beta Z dot? Obviously 0. So what we are going to do, it's already 11:30, so I should stop here because you have classes after this. Any questions up till now? So we have written down in the most general way the trajectory of a relativistic, the acceleration of a relativistic particle in components due to a uniform magnetic field B, okay, in terms of the energy and the charge of the particle. And we're going to solve this equation to get the trajectory. That's what we're going to do next time. By the way, I would say that Landau-Lifshitz is a very good source for this part. So if you want to read a book on this synchrotron radiation, Landau-Lifshitz is very good. Jackson also gives a very competent description. Okay. The only thing is I'm doing it in my notation so that it's completely streamlined with the kind of notation we have been following for the radiation due to an arbitrarily moving point charge. Okay. So is there a question? Okay. In that case, should I say goodbye? So first let me stop presenting.